Great, great. Okay, I think everyone's here, so let's go ahead and get started. Welcome. We're very happy today to have Abhishek visiting us from Maryland to tell us some stuff about QCD Axions. Please take it away.
Let me just check it. Oh, can I?
Now working?
I have to do it.
Is it working last time?
Yeah, I was just trying to see if I can change the slide, but okay. It's fine.
Not too bad.
Sorry. So thank you so much for the invitation. Been to Chicago a few days, but this is the first time I'm at the university, so it's great. And today I'm going to talk about some things about light QCD axions and some effects, some terrestrial effects on experimental observables. Okay, so let's start. It's a very niche topic, I know. So okay, I'll give you a very good intro. But before that, the first question, the first question that I asked myself, that why should I work on axions? And I think for me at least, physics is an experimental subject. And if you just look at all this is so I've taken this plot from this guy's this website. And if you see the amount of experiments that are looking for axions, so I thought maybe why not just spend some time and try to understand what is going on. So that was my motivation. That has been my motivation to work on axions. And yeah, in the green, I think all the experiments that are looking for axions are axion light particles. The red one is dark photon, and some scalar and vectors are in blue. Okay. So that's the experimental motivation. And if I just, a lot of stuff, but what is the physics? And if I just say, okay, what is the status of axial searches here on the y-axis? This is the axion photon coupling, which if you really think of the QCD axions, you can relate it to the axion decay constant Fa. And this is a plot as a function of Mn, the mass of the axion. And I would like you to notice one thing. You see most of the experiments, okay, barring these ones here, most of the experiments, the one in red especially, most of them are in a region which is above this yellow line. Fine. So what is this yellow line? I'll come back and I'll talk about this line. This is the QCD axion line. So that means most of the experiments are approaching the line from the above. So the first question that we should be asking ourselves, that are these experiments, till we get to the line when we have the QCD axions, let's say it's there, are we even looking for any model which are any well-motivated models? So that's why the first question. And the answer is, well, I know only three. And two kinds of models at this moment. So most of these experiments are looking for two models, which is like really an island in the model space if you really think about it. So that's the first thing. And then the second question is, are we even supposed to find anything in that part of the parameter space or not? So that's the second question. Hopefully, I'll be able to, we'll try to understand by the end of the talk. Okay, so these are the two questions that I would focus, we'll be discussing today. So now let's even break it down. Okay, fine. But what are the experiments that are actually looking for QCD axions? I've showed you 3 slides about the experiments, but what are these? And just to make sure so that it's not misleading. If you are thinking of axion light particles, which couples to some FF tilde thingy, then I'm not complaining. All the models, I mean, you can write a model of axion light particles and you're fine with it. My complaint is that if you really think of this is the QCD axions, then are we looking for some well-motivated models? I have no complaints against the axion light particles. That's fine. But if you really think of the looking for the QCD axions, what do people actually look for? So this A over F GG tilde, this is the coupling. This is the defining coupling of the QCD axions. I'm guessing everyone is familiar with this. I haven't even given an intro. And okay, so this really gives you something called an oscillating neutron idiom. Well, That's why we invented it, to solve the neutron-helium problem. And you can look for it through some experiments called NEDM, Caspar Electrics. And you can also look for this particular coupling A over F GG tilde through clocks. And if that's a news to you, you should, I would be happy to explain why. Any clocks or precision spectroscopy can also look for QCD axions, and because of the how does it depend on the hadronic spectrum, but that's a fascinating thing. And the nuclear clocks would be they are going to make a nuclear clock, and I think it will be an exciting few years for us. But the observable that we look at is either depends on the field A and the field amplitude. Okay, that's important for us, just to understand where I'm going. And the another coupling that you can look for, it's because it's a pseudoscalar, right? It has d mu A, j mu 5 kind of coupling. It's in green, and this coupling reminds us of mu dot B, right? So this is that's why they call it a magnetometer. So the axion acts as a magnetic field in some sense. And the experiments that are looking for, they are called magnetometers. Caspar Wins and Nasdaq and some experiment. But the observable that we have is the gradient of the field. Fine. And then the third one in blue is the axion photon coupling. I have showed you the plot. That was the first one. And you can look for this particular coupling through a lot of these experiments, Abracadabra, DM radio, I think they have merged, if I remember correctly, SAFT, everything. And these experiments are looking for the axion field, but it's naively that is true, but I'll come back to this point. And again, for this particular talk, I have in my mind a dark matter axion dark matter. And I'm taking it, I'm making the mass to be very small, and I'm really thinking of it's a classical wave. Okay, there are two people already laughing in the audience, but just bear with me. It's really, really classical at this moment. So that's the setup that I have in mind. And if you really think of the experiments, right? This dark matter solution is there. It's at infinity. It's far from us. And we are doing the experiment here locally. So the first question that we asked, and that's the name of the paper that we wrote with a lot of people in this year, I guess, forgot some point, does matter, or the presence of I'm not sure it's called the Earth, because one Australian guy told me you don't say the Earth, you just say Earth. So I'm not sure, and so please correct me. Is it called the Earth or Earth?
Both sound fine.
Okay, so the experiments are done in the vicinity of the Earth, and so then the first question that we should ask ourselves, does matter, or Earth in this case, matter for experiment? Okay, so that's the explanation of the name of the paper. Fine. So I'll go through all this. But before I dive into the experimental part, I'll talk about the theory and the challenges for the getting a light QCD axion. And my claim is that has something to do with the naturalness, our good old friend naturalness of anything. And because of that, getting a lighter QCD axion is a super difficult QFT question. And every time we go beyond naturalness, we learn something. So in my mind, in my 2 cents, this is a question about the QCD axions, model building. If someone wants to take up on, that would be awesome. At least I don't know of any good models where it even do the job. So what is the problem? And why did I claim that it's a naturalness problem? And this is also the line, the QCD axion line. Why? So imagine, okay, so what is the QCD axions, right? You write a coupling which is A over Fa times GG tilde. Okay, so I can really think of A, okay, some field interacting with some standard model operators, GG tilde, and the interaction strength of the coupling is 1 over Fa. If I don't tell you anything, and if I ask you, okay, can you calculate what is the mass of this guy coming from this GG tilde operator? You'd just use your naive naturalness argument, and you'd be saying, well, the mass would be, it's a dimension 4 operator, so it would be some lambda power 4. I need 2 insertions, so it's 1 over f squared would be m squared, or delta m squared. Or another way to say it, the mass would be the G glue one, whatever is the coupling, times some characteristic scale. Anything that happens in any, okay, there is a caveat to the statement, but if no one asks me, then I'll not explain. But yeah, so, and for any strongly coupled theory, things happen at the confinement scale. So you just put this cutoff to be the confinement scale, right? And what is the naturalness argument that we all know in our life is that given an interaction strength, it just tells you what needs to be the minimum mass of a field, right? So given this interaction is 1 over Fa, all I know what the mass needs to be. Another way to say it, the mass needs to be greater than what I'm getting from this GG tilde coupling. And so Ma needs to be greater than G gluons times this lambda square. Another way to say it, this 1 over Fa needs to be less than Ma over lambda QCD square, right? So from this perspective, if I look at the line here, for all this white part, okay, so this is a 1 over Fa coupling as a function of mass. I just choose a different plot, same guy, different plot just to show the point. Here, this side of the parameter space, the white space, the models are actually natural because naturally I know that my mass needs to be on the line or to the right. That's why if you want to write a QCD axion, heavier QCD axion model, it's very easy. Any interactions would give you a mass, just write it. Okay, of course it comes with the cost of making the hierarchy problem worse and all this, fine, we can discuss about all these issues later. But just if I just focus on the QCD axions, getting on the higher, this part of the parameter space is very easy. On the other hand, this side where most of the experiments are, as we saw before, or even now, as you can see here, the models are super unnatural, right? Why? Because again, I mean, you need to somehow do something to get there. I mean, it's not easy. And how much is the tuning? So this is the delta. I wrote it as tuning, and the tuning goes as how that it really matters how far you are going in these directions, the direction of the arrow. And for mass of, let's say, 10 per minus 10 eV, this line, and the Fa of 10 per 10, so somewhere around here, your tuning is of the order of 10 per 14. So if you really want to, yeah, I think it's a very, if you are, I don't know, for me, it's a great puzzle. I don't know why, it's super difficult to come up with a model. Okay, we did come up with a model, Keisuke had a model, Lanson had a model, but only 3 that I know that does it properly.
What about QCD and null?
Then you will be on the line. No, I'm saying.
It doesn't seem to be very hard.
I mean, on the line, you mean?
Yeah.
I mean, on the line, I mean, the QCD axion gives you
Yeah.
on the line, right? I'm saying if you want to say that, oh, okay, I want to write a model that can be proved by the experiments tomorrow, right? And
lighter ones.
lighter ones.
Oh. Okay.
I mean, we need to make our lives a bit harder. And why is it such a problem? And there are 2 tunings, okay? If you really want to get a lighter QCD axion, usually we look over the second one. That's why I wrote why it is. So the point is, if you know, how do you tune things? You just say that, oh, okay, I have a cosine, I'll add another cosine with a minus sign, fine. That doesn't really work for the QCD axion. Why? Because if you are writing a generic new term, that needs to align with the mass, with the potentials that you're getting from the QCD. So you need 2 tunings. One is the phase. The phase needs to be aligned, and you need to also cancel the height of the cosine potential. Okay, so there are 2 tunings. You need to get, if you really want to get a lighter QCD axion, you need to address how to get rid of these 2 tunings. That's what makes it a bit more challenging. Any random Jew things cannot do. Yeah, fine. So that's my rant about this thing. But now I really want to switch gears. And if you really want to see, I mean, I can show you how to do it in one model where you put a lot of stuff, but you can actually do it. So this is this paper that we wrote with Anson recently. But now I want to talk about what happens if I have some axion dark matter experiment in the presence of the Earth. Okay, and just for us to understand, the similar effect will also be there for any quadratically coupled light scalar dark matter searches. There are many. We pointed it out back in 2022 with Gilad and all these people. There are other Munich people are working on it, but somehow the community doesn't seem to be understanding this part. But okay, so let's say I have the QCD axions. How does it interact with matter? If I want to talk about the matter effect, I should tell you how does it interact. And again, we go back to our old friend, the potential that we started with, and it's really this part. And this is the pi nucleon sigma term. This is sigma n with n bar is the nucleon n represents a nucleon, times square root of some functions which depends on a over fa. Good. And if I just expand it, then you see that, okay, I get a term where the interactions with the axion goes as a square over fa square, sigma n bar times something. Again, this is really not surprising if you know that, okay, the axion is a CP odd particle, right? So at the theta square level or a square level, I would have some interactions with the CP even part. So that's it. I mean, it's just CP properties, nothing else. The Goldstone CP times the Goldstone-ness of it gives you this.
What is Z here?
Oh, this is the ratio of the up and down quark masses. Sorry,
Z.
thank you. Z is m up over m down.
I thought it's the redshift.
Oh, no. This is, yeah, sorry. Yeah, I should have written it. It's m up over m down. I mean, as you can imagine, right, in the limit your m up goes to 0, your axion is not physical, right? So that's why it has to be there, because if I just set it to 0, there should not be any potentials for axions, right? That's the reason. But anyway, so now what we have in a finite density region, this n bar operator gets an expectation value, right? And the first thing you notice is that the axion mass actually decreases inside the medium, right? And so inside the medium, you have some ma squared outside mass minus some delta m squared coming from this expectation when this operator n bar gets some non-zero expectation value. And this is how you can write down. Again, this is not surprising. Why? Because if you really think of the quark masses in a finite density region, the quarks are getting less massive, right? And I know that my axion mass depends on the quark mass. So again, this result, again, everyone knows it. It's all in front of us. But the physics is really that any dense object creates a potential for the axion. So that's the meaning that, oh, my mass is decreasing, so it's a potential well. And if I really think of energy conservation, that means if I'm thinking of some wave coming in, the momentum increases inside the potential well. 101 quantum mechanics, right? I mean, we're just discussing quantum mechanics. So I have a wave, I have a potential well, so the momentum inside the well is more than outside. Great. So the momentum inside Q is greater than K, is actually K squared plus how much the mass is decreased, and that is greater or equals to K. So momentum increase, mass decrease, that's what it happens. Great. But now you can ask me something very simple, be like, okay, fine. It can happen that, you know, if the mass really decrease a lot, and at some point it could be negative, right? Because I haven't told you how much the mass I can decrease. At that point, so something is wrong. What is wrong? That my axion minima changes from theta equals 0 to pi. So whatever I have done, everything breaks down, of course. I need to expand my axion minima around theta equals pi, not theta equals 0. So again, but that scenario is already been ruled out by neutron idiom measurements and lattice study, right? Because neutron idiom is always mod pi. So we cannot distinguish theta equals 0 and pi, both are CP, even CP conserving points. So, right. So that's already pointed out by Anson and Carley back in 2017. Okay, great. So for us, we really want to be in a regime where the momentum change for any density of matter to be important. I want to be in a regime when the momentum change is large. Another way to say it, K is greater than, Q is greater than K. And also there is no phase transition. Another way to say it, that I'm still in a kosher part of my whatever I'm doing, right? I don't want to be a theta equals pi, right? So if I just put it in mathematical terms, Q minus K over K needs to be greater than order 1. So that means delta M, if I just put it here, needs to be greater than K. And delta MA also needs to be less than MN because I don't want to flip the sign of the potential. And as you can imagine from this rough scaling, beta here is the velocity of dark matter, which is 10 power minus 3. So there will be a 3 orders of magnitude when this density effect is important. So delta M needs to be MA times 10 power minus 3, needs to be less than MN. So there is this 3 orders of magnitude. You will see it. So all order 1. But we'll do it properly, okay? I mean, you don't have to believe all my order 1 arguments. But, okay, before I do it properly, I love ENM. So I just want to say that this is something that we have seen from our ENM. What happens? Let's say I have electromagnetic wave coming at vacuum, your refractive index is 1, fine, has some momentum, is coming in, and it's entering a medium with higher refractive index. Okay, what happens? We know at the start, I mean, the field amplitude decreases, right? Because the wave is coming, there is something is reflecting back. A lot of things happen. There are some resonances, but barring the resonances, the field amplitude decreases. Fine, so that we know from our EM analogy. Also, because I'm adding some R-dependent potentials, the gradient effect is altered. Okay, sometimes it enhances, sometimes it's actually enhanced because always there is the potential part. I mean the gradient part. Great. So that we know from our from E&M study. Fine. But let's do it. So this is the equation of motions that we need to solve. So this is when your small r is greater than r, means outside of my dense object, I have no potential. R less than r, I have some potentials, delta m squared, right? Mass change. And I wrote the field in terms of omega is the energy. So we wrote it in terms of the Bessel functions, right? It's a radially symmetric potentials and everything is fine. So we write it in terms of YLM, or in this case, M is trivial. So it's only the Bessel functions, fine. So we solve this. Just so you know, I am really thinking of the dense object as an uniform density thing. Again, we should change all these assumptions as we go along, but at least for this study, we took a very idealistic scenario and we did that. And then what are the observables that we have? These are called the power spectral densities. Another way to say it, you just calculate what is mod A squared. It's the amplitude squared, that's the observable. Then you have the derivative with respect to R. As I said, that there are some magnetometers, so we look at the gradient effect. Also, there is some derivative with respect to theta. As you can imagine, I have R and theta, phi is trivial at this moment. Okay, A0 is the amplitude at infinity. So we would be measuring everything in terms of A0 because we want to know how much I'm enhancing or decreasing. So fine. So these are all the setups that we have. But it's just too complicated, right? We don't make any sense out of it. So let's do something that is not complicated. So we plotted it. So here on the y-axis, I plotted A of omega at R on the surface, divided by square, divided by A squared. So I'm really looking at the change, the enhancement or the decrease. The y-axis as a function of QR, the momentum inside the potential well. For two cases, here the de Broglie wavelength is greater than R, and the de Broglie wavelength is less than R. So the momentum outside de Broglie wavelength is 1 over k. So kr is less than r, 1, which is 0.1 here, and here it's 10. So these are the two cases. The first thing you notice that here, so the blue line here is L equals 0 mode. What is this? Orange. So the orange is L equals 1. So we just individually plotted each and every mode, and the actual solution is the sum of everything. Fine. So here, in this particular scenario, when kr is large, we don't see any change. There is no enhancement. No, it's roughly 1. I mean, there is nothing going on. So yeah,
what's the meaning of the resonances? The little.
I'll come back to it.
Okay.
So that's important, right? I mean, even for the electromagnetic wave, you see the resonances.
Sure.
Yeah. So this is really, so yeah, that's a good question. See, I have some formula. Okay, I'll come back. Yes, we are also surprised. So as you see, right? So for some values of this Q, there is some resonance, and then there is an enhancement. And the enhancement is of the order of 1 over kr 12 plus 2. Let's match it. For L equals 0, it's 1 over kr squared. So this is 100. For L equals 1, it would be 4. So it's so this is this one is the 1 mode. So it's a bit more than 4. So roughly there are some factors of 3s and 2s and blah blah, but roughly this is what is happening. And as you see, right, I mean, because it's a resonance, the width decreases with a higher L. Of course, because the resonance is, I can really think of a delta function. So the height is 1 over the width. Okay. So if my height increases, another way to say is if I'm getting sharper and sharper, then it would be the width is smaller and smaller. Fine. Okay. But if I just but the resonances are not that common, right? Because they are not really. It's not a generic feature. What is a generic feature is that there is a decrease, and that decrease in the field amplitude is damped, and the damping part is kr over qr square. We need to do a bit more math to understand this part, but this is how it goes. And this is shown by the gray line. the big gray line over here. Okay, so that's what happens. So my gradient, sorry, my field amplitude on the surface of the Earth is actually damped. It's suppressed compared to what I would guess. And so so what happens? So let's take one mode for your question. For example, let's say L equals 0 mode. So for L equals 0 mode, the mode function looks like this: A0 over minus 1 IKR plus QR cotangent QR. As you can see from here, for cotangent QR, for QR to be pi over 2, this term goes to 0. Right? So my amplitude is A0 over KR, and my KR is small. So this is the enhancement that you see for the resonance. So exactly this is what is happening. Okay. Right? Okay. So that's what I'm sorry. Forgot to change the slide. But when cosine QR equals 0, I get it. I get something. So, but what is Q? I'll come back. So the Q means there is some value of FA. I'll come back to this in the next slide. But you can ask, okay, what happens when my Q of Q times R is small? Another way to say it, there is not really any momentum change happening inside the body or outside. In that case, QR times cotangent QR is 1, right? Because cotangent X goes as 1 over X for small x. So X cotangent X is 1. So this is 1. So there is nothing happening. So there is a region when these things happen. That I'll show you in 2 slides. So the amplitude decreases when Q is greater than 1 over Q times R is greater than 1. And when I have some appreciable change in my momentum. Because if K is small, we saw it before, nothing happens. Okay. Okay, so whatever the resonances, should we take them very seriously? So what we plotted here for different F values, we plotted the field amplitude square. And you see, right, for some values of Q, means some values of FA, I do see some resonances, but the only important one is the last one, because the other ones are really, it's like a line, we don't get to see anything. Has some small Q dependence, but it's not really important. So if we are really lucky, and if we are probing an F of 2 10 power or 3 10 power 3 times 10 power 13 GeV, then we may get to see some enhancement in the experiments that are sensitive to the field amplitude square. Otherwise, we are in bad shape.
So R is
the size of
chunk of the size of the chunk of matter.
R we have taken because it's a R is the radius of the Earth.
Radius of the Earth.
Yeah.
But actual detector is somewhere on Earth, right? I mean, there's only in some direction you're seeing the radius of Earth, in some other direction you don't. Right?
So that's why we averaged over theta, as you see, right? I mean, we are integrating over all theta phi directions.
Oh.
Yeah. Yeah, that's what we are doing. You are right. I mean, if you are, it will be, yeah, if I am not integrating over theta, then it's a different thing, but we are integrating over theta. Yes, but again, see, as I was telling, right, we have taken the density to be uniform density, right? So it's some rho naught over 4/3 pi r cubed. But of course, there are some inhomogeneities, and you need to take into account the atmospheric effect and all these things. If you take those things into account, the resonance actually changes, because when are you having the resonance? When the momentum of inside the potential times R is some value, right? And that depends on how good are you, I mean, you know, how good you know your momentum inside. That depends on the decrease of the axion mass. That requires us to know the density profile. So
this is taking some fixed strength of axion nuclear coupling.
We have taken it to be 40 MeV.
Huh?
40. I mean, you mean the sigma?
No. Just this. So you're parameterizing as Z over.
No, the Z is M up over M down.
No. But the coupling between the A and the sigma N is the.
Yeah, sigma N is the nucleon, pion nucleon this is the nucleon sigma term, right? That we can get from the lattice study. This is the matrix element when you have, yeah. So that it's I think it varies from 40 MeV to 60 MeV. So yeah, so we have taken 50 MeV, I think. It's just something in the middle. Yeah, it's the
I guess what I'm getting at is, does this assume some coupling between the axion and the nucleons that to be some, or this is the,
no, this is really no, we did not. It's just we started with the GG tilde. And then we went to the hadronic spectrum. We expanded in terms of expanded those terms.
this is coming from the pi naught mixing?
This is coming from the point.
Oh.
Yeah, I should have mentioned all this, but yeah, so the thing that we see here, the blue line is when the damping effect is happening. And as I told you, right, I mean, for Q times R is smaller than 1, there is nothing. So it's only in the blue shaded region there is some effect. Inside the red shaded region, your theta becomes pi. Fine, I already discussed that you have the mass decrease so much that we have we have a phase transition. And then you see this roughly these 3 orders of magnitude between from, let's say, 10 power minus in the mass 10 power minus 13 eV to roughly 10 power minus 10 eV. And this stretch, you need to believe me, that's the 3 orders of magnitude where things are important, where things are interesting because of the momentum, as I've already shown before. And again, there is no effect here for the amplitude, but there would be something later. But as of now, this is what we have.
But this is coming from, the exclusion is coming from neutron EDM,
In the red, yes.
but in the neutron EDM measurement,
Mhm.
do they also suffer from this matter effect? Or?
I mean, at that time, as I said that, see, I was expanding the thing.
So theta equals pi only.
See, I expanded this guy
Huh.
in theta close to theta equals 0, right? Because
Right.
this is sine squared theta bar plus A over FA.
Right.
And then I have said that A over FA plus theta bar, I mean, wave of A over FA plus theta bar is 0, right? But if I am in the regime when this term is super large, that means I am minimized at theta equals pi. So this expansion is not valid.
I'm guessing I have a little bit, I'm just probably just confused, and because I thought this is a local coupling between axion and the nucleon, right? You're sensitive to local nucleon density.
Right. But the local, the local nucleon density, yeah, that's
Isn't this just depends on your nucleon density in your lab, or?
I mean,
when you do the EDM measurement.
When you do the EDM measurement, if I, first of all, okay, I should be a bit more careful. This matter effect that I was telling you about, right? It's strictly for, I mean, if you have an incoming wave, right? So it's for a wave thing, right?
Yeah.
My neutron EDM bounds,
yeah,
they do not care about.
They just talking about your
yes,
your local axion.
Yeah, it's
where is it? But I thought that was mostly just depends on this coupling is a local coupling, depends on your local nucleon.
Yeah, that I agree. So the range of the parameter space where my theta is pi, my analysis does not apply. That's what I would say. They are better. I mean, they are much more sane than us, I would guess, right?
I'm just wondering whether if I'm doing a neutron EDM measurement in the lab, should I think the A is at the A mass term still inverted or not?
If I'm doing a
locally, my local axion, I thought it's still 0, around 0.
What inverse axiom mass you consider? E length.
axion mass.
Inverse the axiom mass.
Oh, right,
In
yeah.
length
Um,
unit.
So that's
That
that's in the
much
plan.
larger than R size.
So this is when your so K is ma times beta, right? So here it's 1 over R. So 10 power minus 13 EV is 1 over the size of the Earth, right? Now I think what Lianta was asking that
The axion is the mass is a.
Hmm?
Axion mass is a.
so if my axion mass is 10 power minus 13 EV, so 1 over the mass is the size of the Earth.
Ah.
So that's what KCP was asking, right? What is the
So I guess he wants to say that then you have to average over
yeah.
Earth.
Or I would imagine maybe we can in principle solve the position axiom equation state, equation motion for position dependent axiom.
Yeah.
Yeah, that
So
you
maybe there, even if there's a vanishing density here, there may be leakage from the core of the R, so that the theta is non-zero actually around here.
so there you get a
Profile.
profile. There you get a profile which interpolates from pi to exponential minus R over m times R, right? That's the profile that you would be getting, Yeah. right? So when you
Yeah,
go from
but does this translate into the neutron still?
does this, I
Yeah,
mean,
when I'm doing my neutron EM experiment in the lab, is the theta equals what?
I to be honest, I think
My local axion is what? Yeah.
I think the local axion effect really does not the local thing does not get affected, at least in the analysis that I am doing here.
Sorry, if the local thing does not get affected, there shouldn't be then there's no limit on the neutron EM.
No, but why?
If my local axion is still my axion in empty space.
Sorry, what I meant is maybe I need to rephrase myself. What I meant is, see, so okay, can I take a step back?
Yeah.
I'm saying the following thing. Okay, I'm saying if you're let's just forget about this. Like I'm saying, just let's focus on the red thing first. Okay, if I choose one FA of 10 per let's say 12 GeV or mass of 10 per let's say 13 EV somewhere here.
Right.
In this case, if I just calculate, if I go back and if I calculate what is the delta MA square, right? Just calculate what is delta MA
As a function of position.
as a function of position. As for this particular F and M as a function of positions, if I calculate it, I see that my my potential is flipped, right?
Not everywhere.
As a function of positions, right?
As a function of position.
So it could be flipped here. It could be
not flipped in empty space, right?
Not flipped in empty space.
But flipped in maybe deep inside Earth.
Yeah, but I'm not doing the experiment.
So that was my question. Is it but I'm doing my experiment on the surface of Earth.
Yeah. So what I need to do in that case, if I want to take your effect into account, I agree. Then I need to expand my potential, or as a function. I mean, not around zero, but as around this the profile that I have, R dependent profile. Then I do the analysis. So if I am, that's what I was saying, that if I am in this red part of the parameter space, I need to be more careful and I need to take this into account. But if I'm not in the red part of the parameter space, I can do what I did, this one, or I mean, this zeroth order thing, and then get on with it. But your question is actually, it's really important, and we thought about it that it doesn't apply there, but I'd be happy to. Yeah, we were thinking actually how to. I think this was one of Gilad's question, was how to reinterpret the neutron idiom bounds, right? Do we get rid of them or not? And then the answer was, well, we need to actually study more. So
that's a really question. For theta equal pi exactly, but is there a neutron idiom bound?
No, because neutron idiom is always mod pi, right?
So then why did you mention idiom bound rather than?
No, I said in conjunction with my lattice study, because my neutrons, then my nucleons would be lighter, right? If theta is
so then it has nothing to do with neutron idiom. Rather, it is a spectral measurement. or just consistency with the lattice computation?
Yeah, so I said neutron idiom in conjunctions with the my lattice study. So yeah, I agree with you.
I guess neutron, he means neutron EDM fixed theta equal to pi or something. I don't know.
No. So the point is when you do the neutron idiom measurements, right? You always look at theta minus pi. I mean, sorry, theta mod.
All right, again, let's forget about this, like in empty space.
Right.
Right, theta equals to pi, is that excluded or not?
In the empty space, if you are, I mean,
I will do this in some vacuum.
no, I mean, if you just, let's say, forget about empty space, anywhere, if you just do a neutron idiom experiment, right? Yeah, so theta could be pi there. I mean, there is
It's
nothing.
not excluded.
Yeah, not excluded.
Right. But what is excluded?
So the point is, if your theta is pi,
Uh-huh.
then I change my nucleon spectrum, right?
So it's really a spectrum experiment.
Yeah, so you
Okay.
need to add both, otherwise you're not doing any
Okay.
experiments. But yeah, maybe I should just say that looking at the hadronic spectrum, I
Yeah.
excluded. Okay, that's probably a better statement, yes. But yeah. Okay. Okay, so that's the first part. And what about the gradient effect? That's the second thing, because we had a lot of experiments which are looking at the gradient effects. And not surprising that the gradient is enhanced. Okay. And again, I plotted the same thing. Kr is less than 1, Kr is greater than 1. De Broglie wavelength is large, small, fine. Did the same thing. Why am I saying it's not surprising? Because, you know, in the end, what is this potential well that I created? It's actually an art-dependent potential, right? So that means there is some sort of new profile that I did not have before, new art dependence that I did not have before. So I had something. Also, if you imagine naively, if I did not have the potential well, then my momentum was k, right? Because I had this potential well, then it is q. And as I said, that q needs to be greater or equals to k. So of course, that either the gradient is enhanced or it is not changed. It is not suppressed like the other thing. Okay. Okay, so this is the structure. Again, I see some resonances and everything. And why resonances? Okay, let's just try to understand it again. Right. So again, I took the n equals 0 mode because that's the most prominent one. I take a derivative. And what I see that for QR to be pi over 2, just say pi over 2, then all the cosine terms are 0. The sine is 1 over kr. And if I just measure it with k, because that's the momentum that I had, then it's 1 over kr square on resonance. And off resonance, when QR is order 1, I still have an enhancement of 1 over kr. Fine. So, and if I do the square of it, because that's what we look at in power spectral density, then it's 1 over kr power 4 and 1 over kr square. So, great. Another thing that you notice here, which was unlike, which did not happen for the last thing, that even for QR to be less than 1, for the amplitude, we did not find any effect. It was all the same. But here, it's actually enhanced by QR square over KR. Again, you can just expand these expressions and we can see it, right? So the gradient seems to be most economical thing for the axions, for axion searches at this moment. And this is what happens. So we are saying that all the grad A effects are, they are affected, they are enhanced in all the regions, which is in the, again, by the green, yeah, it's enclosed by the green lines, okay. So now you see that there is an interesting part where my gradient is enhanced in this triangle by the blue, red, and green line. When my gradient is enhanced, my amplitude is damped, and I'm still, I can still do my math and what I did without worrying about what Leonta was pointing out, that, oh, you have a field-dependent profile and I don't have to worry about. So this triangle is the triangle where things are really, really interesting. So that I will keep in mind and come back to. And then you can also do the same thing. Okay, so this is probably will partly answer your question, how fast this effect dies off. You can just do the same thing and you see that, oh, the effect actually disappears at a scale, which is the de Broglie wavelength over the size over the de Broglie. So if you really go like, I don't know, twice the Earth in these directions, we're not gonna see anything. So that's what the left plot is telling us. I have 10 minutes. And I really want to talk about the experimental implications. But yeah. Okay. Great. So fine, enough things, but in the end, we want to come back to our life and see what actually has changed or anything has changed at all. So as I said, that the magnetometers, the grad A observables, they are enhanced because the gradient is enhanced. On the other hand, all these experiments that depends on A or A square observables, they are suppressed because the field amplitude was suppressed. What about the axion photon coupling? I'll come back to this. This is a complicated story and wait for like 3 more minutes. Okay, so here I'm showing a plot of the axion nucleon coupling, GANN. So this is d mu A n bar gamma mu gamma 5n times as a function of the mass of the axions in EV. This is in GeV inverse. And as you see, the previous bounds, I mean, the existing bounds are in solid colors, okay? And if we incorporate the enhancements that we have shown in the dashed line. So for example, if you take this red line here, if you add the enhancement and multiply by it, then the new bounds would be the dashed line, the dashed red line here. So yeah, accordingly, everything will be shifted downwards, which is great. But right now, even with this enhancement, we are not at a point when we can actually we can probe some uncharted territory. Not yet, but if they can improve so let's say they take this red line. I think this red is Kasper-Zulf. I think it was the flagship experiment proposed in 2013, right, Kasper, at that time. And if they improve their sensitivity by, I don't know, 2 or 3 orders of magnitude, they would have been from 10 power minus 3 to 10 power 6, 3 orders. Here now it would be from 10 power minus 12 to, 10 power minus 15. So we'll probe something new because of this enhancement that we should take into account. So that's the statement about the gradient effects. Again, we are very far from the canonical axion lines. Are we looking for a model or not? Is this anything interesting? Again, talk to your model builder friends or us. We'll see what happens. Great. Okay, what about the axion photon coupling? I have been putting this off for like almost the whole talk. And so the first thing you notice, right? What does it do? This FF tilde coupling, it actually modifies the Maxwell's equations. Fine. How does it do it? So now, in the presence of this coupling, I have d mu f mu nu instead of 0. Right? I have this extra term, which is d mu a times f mu tilde. And of course, the derivative on f tilde mu nu is 0 from the Bianchi identity, right? So we don't have to worry about it. And okay, what does it do? If I just write it out explicitly, that means I have some d dt minus grad b, grad cross b is it now it depends on a dot b, if I just explicitly write it, times grad a cross e. Okay. Now naively, without all these effects, you would say a dot is mass times a, fine, and grad a is the momentum times a, and the momentum is mass times the velocity times a. If we have dark matter, this velocity is very small, 10 power minus 3, and because of that, not the current experiments, they just don't care about this grad A cross E term because of this particular scaling that, oh, it's suppressed by 3 orders of magnitude. Why should we look for it, right? So in the usual experiments, what we do, we have the background electric field, set it to 0. We put a magnetic field and we just try to peek out the axion, right? Axion induced electric or magnetic. That's the setup that we have. But now the gradient is enhanced. So grad A is enhanced, A is actually suppressed. So maybe we need to actually change the strategy of looking for axion photon coupling. Maybe it's better if we just put a background electric field compared to magnetic. If we say this to our experimental friends, I did try to say that, but then one guy really laughed at me and saying, you have no idea about the experiments, which is true. So the question is, you cannot just change your setup, right? Fine. So let's say I keep my electric field, background electric field to 0 and background magnetic field to be not 0. That's the experiment. So now let's see how do we actually pick up the signal from the axions, right? So these are E1 and B1 are the signals that you pick out from the axion induced electric field and axion induced magnetic field, respectively. And B0 and E0 are the backgrounds that I'm putting in. Fine. So this is how the signal looks like. You just take the Maxwell's equation, do it twice. This is what you get. And the signal really looks, I mean, okay, given that you have an apparatus with length L, this is how it looks. Fine. So again, if you just look at it, even if I just set all the E0s to 0, I have only the B0, right? It seems like, okay, naively, again, okay, so we are in the limit when mass times this small l is much, much less than 1, right? Because L is this much, M is large, or 1 over M is small, so this is a small number. So usually people say that, oh, I put a background magnetic field and I peek out an axion-induced magnetic field, right? That's what they do in this experiment. This is because if you just do the analysis in the limit M times L is small, you would see that E1 is much, much less than B1, naively. But here, because you have this grad R squared A effect, this scaling doesn't hold. Because of the gradient is enhanced and my electric field is actually sensitive to the grad square of it. So even with the current setup, we should try to pick out the electric axion-induced electric field compared to the axion-induced magnetic field. Okay? So may need to also change our signal reading setup, even for the given whatever we have. Right? So that's the second layer of argument. Someone might say, well, maybe, I don't know, I don't want to do this. Fine. So the third thing that you can imagine, let's say that I'm not doing it. Forget about that changing setup, anything. And I'm still looking at the B1, picking out, putting a magnetic field, picking out axion-induced magnetic field, this one. Even for that, usually you just drop the grad R, del R A term, right? But that's not the case, right? Even if you do this, because of the now A has a profile and it has some sort of a minimum and the maximum that I have already showed you. So the correct signal is not what we are actually representing. We need to really just, if we want to say that, okay, how much I'm changing my axion photon coupling, given the current setup, I don't want to change anything. It would scale like some C gamma, some factors, alpha over 2 pi f, fine, times the minimum of 1 comma fa over fc that I showed. So existing limits on this, on the axion photon couplings are not really correct. Even if I keep all the setup, keep everything that people are doing, it needs re-evaluation. Okay. I don't have time to show it, but I think I do have a plot. Oh, sorry. Let's see. Yeah. So the bounds will look like something like this. Okay. The depending on how far you are, you can actually change things on this. I would be happy to chat about these things later, but I want to really, I think I'm on time, right? Yeah. Okay, good. So just to conclude, I think I have showed you that, okay, fine. If you're thinking of light QCD axions, obtaining one is very tough. And I'm not even sure, okay, I know only 3 models where you can actually do that, or 2 and 1 variant of it. But fine, given that, the matter effect on the QCD axion, light QCD axion searches are actually important. And I have given you 3 examples, or 2 examples and 3 experiments to demonstrate all of these things. And maybe it's better to look for new experimental strategies if we are thinking of going down this path. I think that would be a good way to end my talk. We need something new. Thank you so much.
Are there questions for Abhishek? I have a question.
Yeah.
On page, can you go back to the, I think it was like page 27 where you showed how the sensitivity is enhanced?
27?
Yeah, sorry, just very dumb question. Could you just like walk through how the sensitivity is enhanced, like roughly estimating the amount that it gets enhanced by, like just for like the Casper and curve or something? Like, can I back up the envelope, just how much it gets enhanced there?
Yeah, so for that, so as you imagine, let's see. So this is really the point where you are off resonance, so it's enhanced by 1 over kr squared, because it's 1 over kr. Okay, that would be the enhancement, and yeah, so take the mass, right? And then multiply by, so KR is 1 here. So if you are going down this much, right?
Yeah.
Then it would be roughly 5 orders of magnitude. Yes, and sorry, or is it 1 over KR square? I forgot, but yeah, I forgot.
It's just counting powers of KR.
Yeah, it's just counting parts of QR square over KR, I think, or
Gotcha.
yeah, I think in this regime you need to just count 1 over KR square. I mean, how many parts of K and R we have? It's just yeah, just put a function of F, right? I mean, because everything is changing. F is down up there, so yeah. It's just yeah, I should have put the formula. But yeah, it's just easy counting. We can do it after the seminar if you are really up for it. Yeah.
So there was a plot where you were showing some enhancement of the axion of the axion amplitude as a function of f.
Axion amplitude as a function of f.
But you were saying you were averaging over theta and phi. Yeah, this one. But no, sorry, not this. Oh no, sorry, it is that one, no?
Okay.
Yeah, and then but here you were saying you're averaging over theta and phi.
I am averaging over theta and phi.
So if you don't do the averaging over theta and phi, then certain experiments looking for certain f's should point like in you know in certain directions towards the earth, and then you can find that function. Like if I want to look for one particular f, is it best to to point along some chord through the earth or something?
See, the point is, okay, what we have taken, I mean, we're really thinking of, if you really, okay, so our starting point is the wave that is coming to us, it's a plane wave, right?
Mhm.
And yeah, so it has this exponent minus I k dot r kind of profile. Fine. Now, this whatever this r theta dependence, phi dependence that we are inducing because of an r dependent profile, right? Because I have a potential which depends on only the radial coordinate, right? I'm not changing anything in theta phi dependence, right? So that's the setup that we had in mind. Now, here, I'm not sure that averaging over theta and phi are actually changing any of the resonance structure. If you're looking for a gradient towards theta, that's a different thing. But if you are really looking for the amplitude, right? If your experiment is sensitive to an amplitude, yeah, so I think the same thing would be to say that, oh, my dark matter can come from this side, this side, this side, and I should actually average over everything. And that's the idea that we had in mind, that, oh, maybe that's the most important way to go about it, but maybe not. I mean, I just, yeah. But yeah, I find it very difficult to believe that, oh, if it has a directions, maybe yes, but yeah, without a stream-like object, then I can imagine, but it's really, yeah, it's just a passing wave, right? So physically, it did not make much sense to me, but I'd be happy to understand your point, of course. But yeah, I mean, yeah. But if you really think of, I think I have a plot. If you really think of the gradient, going to a different slide. If you really think of the theta dependent gradient, that if you are, let's say, sensitive to some experiment, something that depends on the theta component and the gradient of that, along that component, that actually is not enhanced, it's actually suppressed. And there are some resonances, fine, but they're really, really small. So, but that's a different observable. There, you're not supposed to average over, I mean, we did the average after taking the derivative, but again, you see that, okay, it's a different, completely a different observable case. Yeah.
Just a very quick naive question. What is the typical value of delta MA or delta MA squared FA squared around Earth?
I mean, it depends on your FA, right? I mean, because delta M is.
Yeah, so the product MA times FA, for example, then that is something that only depends on the nucleon.
Let's see. MA times FA?
Yeah, the correction delta MA times FA.
It's something I can leave in mind. Let's see.
Yeah, I'm just trying to see how much larger Q is compared to K, basically. That's the goal there.
Oh, if that's the goal, then we know the answer, right?
Okay.
Because see, QR is pi over 2 and KR is 0.1.
Okay,
So just take the ratio. It's pi over 2, so it's pi over 2 times 0.1. So this is
1 order of magnitude.
yeah, it's a factor of yeah, 10 is. So yeah. So that's if okay, that's the goal, then yeah, we know the answer. Yeah, but if you want to really do it, I mean, it's very easy. I mean, we just you replace this sigma n bar as whatever 30 MeV times the density of nucleons divided by 5.5 grams per centimeter cube divided by the mass of the nucleons, so GeV, and Z is half. So that's it. I mean, that's the computations. It's very easy. We can even do it in mathematics, but that's how it is. Yeah. Any other questions?
There's no more questions. Let's thank Abhishek again.
In principle, increase the photon coupling. You don't have to